Hello, everyone.
Yes, ma'am.
Yeah.
We are live, ma'am.
Okay.
Good afternoon, participants. Welcome to the live doubt clearing session of the course Introduction to Multi-Agent Systems. We are pleased to have Professor Twinkle Tripathy, ma'am, with us today, along with our TAs, Mr. Pradeep and Ms. Aditi Saxena. We encourage the participants to join in and clear all your doubts. Thank you. Over to you, ma'am.
Thank you, Mr. Murli, for the introduction.
Thank you, ma'am.
As mentioned, I'll be clearing all the doubts that you have post the topics that we discussed in the previous live session. So to start with, what I'll do is, some of you have already asked a few questions. So let me read out the questions and try to answer them. So the first participant who has asked questions is Wu Tian. So the question that has been asked is, when combining formation control with consensus, how can we ensure not only velocity consensus, but also position and orientation consensus? How is this principle typically applied in real systems such as UAV light shows? Okay, so the answer to this is whatever formulation we have discussed so far pertaining to consensus, the rules are more or less the same. We can use separation-based rules or adjacency matrix-based rules. And there's a very good survey. Let me share a link for that. Yes. So the specific questions that have been asked pertaining to the live session.
Yes, ma'am. We have received few questions via Google form, ma'am.
Yes, so I'm trying to answer those questions.
Yes, ma'am.
Yeah. So I've sent a link in the chat window, and in that link, I've tried, so that link is of a survey paper on formation control. So of course, this course is on Introduction to Multi-Agent Systems. So we have covered most of the basic rules. However, if any of you is interested in more general formulations, then please refer to this survey. A lot of the specific design aspects for different models have all been discussed in this survey paper. Okay, moving to the second question. Regarding the mathematical formulation, do I need to invest significant time in studying graph theory more deeply? And which core concepts are the most essential for MAS research? So, speaking based on the fundamental aspects of multi-agent systems, whatever knowledge of graph theory is required for just to get started with things, all of it has been covered in this course. So you do not need to study any further graph theory or take any other graph theory course just to understand the basics of it. So whatever has been covered in the course is sufficient. I'm particularly interested in cluster consensus and matrix weighted graphs. In practice, when we cannot arbitrarily design the network architecture, how feasible is cluster consensus? Okay, there's something in the chat. So again, all of these are questions pertaining to, I see Dat Bo has asked some more questions on formation control. Please take a look at the survey paper. So in the lecture, the idea was to introduce just the basics of how formation control can be designed. But again, the intricate, of course, there could be a variety of shapes that can be achieved for various kinds of kinematics of the agents. All of these things have been covered in the survey paper. Okay, coming back to this question. when we cannot arbitrarily design. Okay. Again, cluster consensus is also a very interesting topic. Okay, so the question has two parts. First one is about cluster consensus. As the second one is about matrix weighted graphs. So in matrix weighted graphs, what we do is, let's say in general, the edge weight is a scalar. However, when we look at matrix weighted graphs, these edge weights tend to become matrices. So how are they useful? Why do we even do that? The idea is generally, let's say if we look at a particular system, a system could have many entities of interest. So in order to incorporate all of those parameters to a particular agent, we introduce the edge weight, which tells us, how the agents feel about their opinions or their states about all of these parameters. And what are the rules for consensus? So again, the fundamentals remain the same. The idea is that if we want to achieve consensus, then we must ensure that the system reaches the consensus subspace. Of course, it's a subspace. And then we need to make sure that that particular subspace lies in the kernel. So that, whenever we converge to the state pertaining to the zero eigenvalue, the corresponding eigenvector should only be the consensus vector. As long as we can guarantee such a thing for matrix weighted graphs, again, it will lead to consensus. So meaning we typically have to consider few more aspects. That is, not only should the edge weight satisfy some constraints, but each matrix associated with the edges must also, they should not lose rank. So that is the basic idea. If we ensure this, then again, we can ensure consensus in matrix weighted graphs. Yes, so in a matrix weighted graph, we assume that the state vector is multidimensional. So that is why we have a matrix associated. Just a moment. How do I see the chats here? Yeah. So now coming to, so yes, the idea is it is multidimensional. But I only want to design consensus for some dimensions. Okay, so then again, the answer is very clear. What should be done? We should, so let's say there are a few parameters. So what I can gather from here is, suppose each, let's say the dimension of each matrix is P cross P. Then the total vector is N, like NP cross 1. That would be the dimension of the entire state vector. Now suppose what we want is, for each agent, we want only few of the states to achieve consensus. Then all that we need to do is we must make sure. So this is actually a more relaxed condition, because now we don't really worry about what happens to the other states. They may achieve disagreement or they don't, but the two states which actually matter to us, we must make sure that the consensus subspace, or whatever the new subspace is, which ensures consensus of only these two, that must appear in the null space. Okay. Okay. This next question is about barrier-Lyapunov functions and safety constraints. Yes, it is true that barrier-Lyapunov functions are very useful when we want to introduce safety constraints. Just to give a few examples, safety constraints could be in terms of, say, collision avoidance, or if there's a certain region that we do not want to cross over. All of these constraints can be incorporated using barrier-Lyapunov functions. So the key idea remains the same. In general, when we design Lyapunov functions, we say that its behavior near an equilibrium point should be such that the function v, which is a Lyapunov function, must remain positive definite, and its derivative along the trajectories should be negative. So again, if we want to achieve collision avoidance, or we do not want to cross over a certain barrier, What can we do? We must make sure that that particular barrier, at that value, the Lyapunov function achieves infinite value. And inside the good region where I want to stay, there v dot is strictly less than 0. What will happen if we do that? In such cases, it is guaranteed that we will not go towards the boundary of it. So the idea is that this is actually a very interesting design method. All that we are doing is, even in points which are not really at infinity, even at those points, we are making the Lyapunov function to take infinite value. So just to give an example, let us say, I can write it in the chat window here. Suppose we write the value ln x by some desired value xd, or some region, maybe not desired, or maybe we want to avoid that. So okay, let's see that a few questions have already been asked. Okay, so anyway, this is one example of a Lyapunov function. We can see that when x becomes equal to xd, okay, not really this. Let us look at some more interesting problems, and I'll also attach a paper with this. See, again, the specific questions that are being asked, they can be derived using the results that have already been discussed. So consensus has some very basic rules, and we need to make sure that the system goes towards the consensus state. How can we ensure it goes towards the consensus state? We need to make sure that that is the only vector, right? The span of it is our null space. Okay, before we move on to a new topic, let me share a paper on barrier Lyapunov functions. I just remembered a So that's a very good paper which introduces all these notions for the case of formation control problems, which seems to be the interest of some of the students here. So let me share a link of this paper. Just a moment. So please refer to this function. This function introduces how barrier Lyapunov functions could be used for phase synchronization of agents. Oh, you've not received the link. So this is the link of the paper. So let's look at some more questions. So again, the research community has worked a lot on barrier Lyapunov functions. So please feel free to take a look at them. Let's move on to the next question. Okay, the next question is about distributed MPC. Is it possible to maintain the original optimal control structure and only modify the cost or constraints to reflect neighbor interactions? What are the biggest challenges when scaling up or dealing with communication delays? And what strategies are commonly used to reduce complexity? Again, so these are very specific questions. Please refer to the existing literature. Even in terms of delay in general, so delay has also been explored, and you can do it very easily from the topics that have been discussed in the course. Okay, so the question says, in scaling up or dealing with communication delay. Yeah, so eventually we end up arriving at, so okay, when can delay affect us badly? When we do not get consensus, when we deviate, let us say our objective is consensus. If the delay ensures that the eigenvalues now move to the RHP in some way, okay, or even if it does not move to RHP, or if there's any other configuration in which we move away from the consensus configuration, then delay will work against us. So all that we need to do, we need to ensure that the eigenvalues are always in place. So there's something that's known as a delay differential equation. Please take a look at it. Delay differential equation. And generally people talk about some critical values. Just a moment. Critical values of the delay. Okay. So also, I would rather than directing you to lecture notes or textbooks, please refer to latest survey papers in these areas. And if the area is very new, in those cases, generally we do not have survey papers, but I do not think that the areas mentioned here are really new. So I'm sure that you'll be able to find some survey papers. Which frontier topics in MAS? Okay. So there are many topics in multi-agent systems which would be interesting to look at for a PhD. For example, people talk about the area of opinion dynamics and formation control problems. There are always many aspects of formation control that people still continue to look at, and there are guidance related problems in multi-agent systems. There are controllability related problems and many such similar areas that you can look at. And using tools of AI is something that's getting quite popular, AI, machine learning or RL. These tools are getting quite popular, so something that you can look at. And there are some more questions that have been asked here. To achieve controllability, we must design the adaptation matrix first and then design the network, or design the network and then check the controllability. So if you have the freedom to design the system, then it's a much easier framework, because then you can always design whichever route you take. You can always choose a certain, or rather I would say you can ensure that the system remains controllable. But however, generally we do, for practical systems, we might not always have the luxury to design the adaptation matrix. Okay. Next, there are some questions asked by Satish. Could you give an intuitive meaning of algebraic connectivity in the context of agents working together? Okay. So the answer is that how many agents should we talk to? How connected a system is dependent on the number of edges in the network. And the number of edges in the network is simply related to how many agents are actually talking to each other. So the larger or the higher the value of lambda 2, which is the algebraic connectivity, it simply implies that more agents are actually talking to each other. Working together, so I would not phrase it that way. The reason being that the agents may not seem to be directly working together. However, if the network, say, is connected, then in a distributed manner, they can all still work together towards a common objective. However, we can say that algebraic connectivity ensures that more and more agents actually communicating with each other. Okay, the next question is, how does spectral gap of a graph influence the speed of consensus? Okay. So let me try to write this. I hope my screen is visible. Question talks about.
Yes, ma'am. It is visible, ma'am.
Matrix and its eigenvalues. Let's try to understand in the context of the Laplacian, because we have looked at it in the past. Now, what we can do is we can arrange the eigenvalues in this manner. So if it is a connected graph, I only need to add less than equal to here. Let me write it. The underlying graph, here assuming is connected. Then where does the solution go? Suppose it's a Laplacian flow-based model. X dot of t is equal to minus Lx of t. This implies the solution is, x of t is simply equal to, so e to the power minus lambda 1. But lambda 1 is equal to 0 here, as we can see. This is our lambda 1. So the first term is this, then the corresponding left eigenvector. So if it is an undirected matrix, then we know that you already know a few nice properties. I'll talk about them in a minute. V1. So this is x bar, meaning as t tends to infinity. W2 transpose x0 times V2 and up to e to the power minus lambda nt times Wn transpose x0 into Vn. So why does the spectral gap even matter? So the answer to that is, we know that eventually all of these terms, each one of these terms, so there will be n minus 1 such terms. Each of these terms are going to decay with time. So how fast can we actually reach the consensus state? So why am I saying consensus state? Because here V1 is nothing but, say, 1n. And if it's an undirected graph, I know that W1 is equal to 1n divided by n. So eventually, the entire solution converges to this state. This is the only term which remains. What does that mean? It means that all of the other states actually cause disagreement. And how how fast do the disagreements die out? Now that depends entirely on lambda 2. Why only lambda 2? Why not the rest? Because lambda 2 is the slowest, its decay is the slowest. Hence, lambda 2 is what determines how much time it takes actually for all of the disagreements to die out. That is why we say that the spectral gap is nothing but the largest eigenvalue, or in this case 0 for us, and lambda 2 minus this, in fact. So this is a spectral gap. Now the spectral gap can actually be represented in many ways. So let me retrace this slightly. For a general system, I can call it to be something like this. Either lambda 1 minus lambda 2, which is the Perron eigenvalue minus lambda 2. So I'm assuming that you've asked in the context of, yeah. So if you're only interested in consensus, then this is a spectral gap. But however, in the general sense, people write it in many forms, or lambda 2 minus lambda 1. So this is sort of a normalized form. So this can help us actually compare two different graphs as well. So this is a spectral gap. The next question is, and also I hope you now understand why the spectral, or how the spectral gap actually controls the speed of consensus. Are adjacency matrices just a mathematical tool, or do they also have direct interpretation in real system design? So adjacency matrices tell us the information about which two agents are talking to each other. Meaning, suppose we want to say the adjacency matrix is a static matrix. What we mean is that the agents are always able to maintain their connectivity. When is this possible? Let's say in a real world system, suppose I say that I have multiple robots. Up to some maybe Rn. And if I say that each of them has quite wide field of view, and they can see anything within this field of view. Direction doesn't matter. And further, they move in such a way that whoever they saw before, they maintain connectivity with them. In such cases, the graphs remain static, or rather the adjacency matrices become static. Matrices are time independent. So the adjacency matrices encode this important information on how exactly are agents communicating with each other. Okay. In real system design, so also yet another topic that I'll direct you to would be to Markov chains. So a lot of, for example, the diffuse model. A lot of these designs actually use the adjacency matrix. Communication theory uses these notions a lot. Okay, I see that Neela has asked some questions. How do network dynamics of system help us in understanding collective behaviors in traffic network or robotic swarms? So, for example, if the objective of a robotic swarm is to achieve a certain formation, then formation control tools can be used there. Or if we want to ensure that collision avoidance is guaranteed. So as we discussed before, we can use barrier-like runoff functions as well. Are there any specific conditions under which an individual agent behavior dominates over a group dynamic? So this is a very specific setup, meaning, so we are trying to say, or just to rephrase the question, are the agents allowed to be heterogeneous? Yes, definitely. So the agents can be heterogeneous in every given scenario. It is possible to do that. And what will be the conditions for consensus? So again, the fundamentals remain the same. So all that we have to do, we have to apply those fundamentals to any given scenario. So again, if you have more specific, so within this time frame, we might not be able to look at detailed answers to these, but if you're interested, you can email me and I can share specific links for these things if required. Okay, Akash has asked some questions. Could you explain why eigenvalues and eigenvectors are important? So the answer is here. This is why they're important. What is the intuition behind using Laplacian matrices in analyzing networks? So now, if you are interested in consensus, then, so again, this has been discussed during the lectures as well. What is Lx? Lx simply always leads us to the disagreement vector. Hence, it is very natural to use the notion of x being proportional to minus of Lx, because this can ensure that we can achieve consensus as the disagreements become lower. And also, sometimes Laplacian flows also occur very naturally in electric circuits. So in my opinion, Laplacian flows are a very natural way of designing a consensus protocol. Why? Because of this. Because of this property. Okay, so I've answered all of the questions in these responses. Now, let me try to. Are there any other questions? Let me see the chat window. Jacobian has asked some questions on Lipschitz property of functions in nonlinear controls besides ensuring that Cauchy permissions. So Lipschitz property is only used to ensure that we have a unique solution. The solution exists and it's unique. So it does not have anything to do with the multi-agent framework. So again, Priyanshu, so you asked me a question about the desired consensus paper. So again, the literature on second order systems is quite wide and well researched. So I don't think you would need to use tools like sliding mode control. That, in my opinion, would be overdoing it. There are simpler consensus which can actually do the task here. So we talked about the matrix weighted graphs. Again, all that we have to remember is when we are looking at a second order system, we are saying that the input appears in the double derivative of the state. So then each x is actually represented using, or each agent is represented using two states. So again, the same logic can be applied. Okay, so are there any other questions?
On YouTube also, I checked, ma'am. No queries posted over there.
Okay. All right. So So please familiarize yourself to the fast growing literature in the area, and there are many interesting things to look at. I hope this course has given you a background to now undertake some problems in the area. Mr. Murli?
So can we wind up the session, ma'am, since there are no queries?
Sure.
Thank you so much, ma'am, for this live doubt clearing session. You have explained the answers in a very detailed manner with a lot of examples. It was very useful and informative. And we hope all the we thank all the participants as well for actively posting their questions and making the session very interactive. We are closing the session now. Thank you all.
Thank you.